Hi everyone. I'd now like to do an overview of our work on this equation, which we solved on all reals and also on the interval from 0 to 2 pi. Now, when we were finding the general solution to begin with, it was very helpful to substitute theta for 4x. So then we're just dealing with sine of theta equals negative root 3 over 2, which is a good old school problem. Solve that for theta. We found solutions in quadrants 3 and 4. Now, for quadrant 4, you might have preferred negative pi over 3 as a representative for that point, but since we're eventually going to solve for the angles for solutions between 0 and 2 pi, actually 5 pi over 3 is nicer. See, if you had picked negative pi over 3, then in the later phase of the problem, when looking for solutions between 0 and 2 pi, then after dividing by 4, then in group 2, you would have started with negative pi over 12 here, and then you would have had to reject that right off the bat, and then add pi over 2 to get your first solution, which is fine. You can do that. You could have started with negative pi over 12 as your first solution for x, reject that, and then add 6 pi over 12 to get your first legitimate solution, 5 pi over 12. So anyway, that's why we picked 5 pi over 3 as our representative for this point here. Although negative pi over 3 might have been more convenient if you just cared about the general solution on R, all reals. But basically, this was a pretty generic problem, and our solution set for theta essentially looked like that. Theta equals 4 pi over 3, also the coterminal twins, or theta equals 5 pi over 3, also the coterminal twins. If you were to use Desmos, here's the graph of y equals sine of theta, where the horizontal axis here is the theta axis. It's our sine wave. And where does sine of theta equal negative root 3 over 2? For what values of theta? Well, we look at the theta coordinates of the intersection points. Over here, we see 4 pi over 3, right? That was our quadrant 3 rep over here. We see theta equals 5 pi over 3, also gives us an intersection point between the red and blue graphs. 5 pi over 3 here is a solution for theta. We could have picked negative pi over 3, but we just had to worry about 1 rep in quadrant 3 and 1 rep in quadrant 4. So these were fine. Basically, representatives for these 2 points between 0 and 2 pi, between theta equals 0 and theta equals 2 pi, 4 pi over 3 and 5 pi over 3. But then, we want to consider all the coterminal twins. Now, you might be asking, well, since we're dealing with sine of 4x, can't we just deal with 4 reps for this point and 4 reps for that point? Actually, that's the approach that Ron Larson takes. Many of my notes are based on Ron Larson's textbooks. So Ron Larson might say, okay, take the 4 pi over 3, okay, add 0, take the 4 pi over 3, then add 2 pi, add 4 pi, and add 6 pi. Take the results of these sums, divide by 4, and then you'll get the 4 solutions in group 1 when we get the solutions for x between 0 and 2 pi. But even though Ron Larson is normally clear, I don't think he's too clear in this respect. And in fact, if you use symmetry, or if you're dealing with tangent or cotangent, or if you're dealing with quadrantal angles, then it may not be clear what you need to add by and how to exactly work it out. So I think my method is actually better and clearer. Okay, so we have all real solutions for theta right here. 4 pi over 3 plus 2 pi n, or theta equals 5 pi over 3 plus 2 pi n, where n can be any integer. Now, how do the solutions for x compare, right? Well, again, you can imagine all these solutions, line them up, divide all these by 4, and pick the ones that are between 0 and 2 pi. So that's sort of the philosophy behind what Ron Larson is doing, but operationally, step by step, I think my process is clearer. All right. So what do? We replace theta with 4x, we do our division by 4, and we get this as our general solution set for x. All right. So now we're graphing y equals sine. So now we're considering the original equation, right? And we're considering x. So for what values of x does sine of 4x equal negative root 3 over 2? How does the graph of y equals sine of 4x differ from the graph of y equals sine of x or theta? It's a squeezed in graph. We get 4 cycles where we normally have 1 between 0 and 2 pi. So then we don't get 2 solutions between 0 and 2 pi like we did for theta. We get 4 times as many. We get 8 solutions. And where are they? At pi over 3, 5 pi over 12, and so forth. We get these 8, well, let's put them all out. We get these 8 solution values for x. These 8. These 8, from pi over 3 all the way up to 23 pi over 12. These 8 x coordinates for these 8 intersection points between x equals 0 and x equals 2 pi. And these 8 solutions are the ones that form our ultimate solution set over here. The 4 from group 1 are the ones on the downswing. So 4 pi over 3 went to pi over 3, okay, and also 5 pi over 12 and 2 others. Oh, okay, wait. So pi over 3, hold on, not 5 pi over 12, sorry. It's pi over 3, and then the 5 pi over 6 is over here. So here's pi over 3 over here. Here's 5 pi over 6 over here. Okay, so pi over 3, 5 pi over 6, 4 pi over 3, so pi over 3 over here, 5 pi over 6, 4 pi over 3 is hidden here. Okay, and then 11 pi over 6. All right, these were the guys on the downswing, And all 4 of these guys came from group 1. They ultimately came from, this spider egg over here. So on the unit circle, if you were to look at our 8 solutions on the unit circle, our solutions for x, we have a lot of them. It's quite a mess. So our purple solutions for x in group 1, all right, they corresponded, I should have put this in purple. They came from this purple spider egg for theta. Remember, these are our solutions for theta. 4 pi over 3 plus 2 pi n, also 5 pi over 3 plus 2 pi n. These 4 purple spiders came from this purple spider egg. I'll actually color them in purple. This purple spider egg in quadrant 3. Whereas these red spiders, these 4 red spiders, come from this red spider egg in quadrant 4. Notice if you look at the solution set, the ones from the purple spider egg in quadrant 3 for theta, so the quadrant 3 spider egg for theta gave us these 4 solutions for x. Oops. In purple. These 4 spider eggs for x. And then this red spider egg for theta in quadrant 4 ended up giving us these 4 spiders for x in group 2. Notice the purple eggs over here, the purple egg over here is less than the red egg over here. So that leads to the fact that this purple spider is less than this red spider, and so forth. So the group 1 angles are a bit less than the group 2 angles. So again, the 2 solutions for theta, remember we just had 2 solutions for theta at 4 pi over 3 and 5 pi over 3, all right? Imagine the spider eggs here. So we consider their coterminal twins. When the spider eggs break up, okay, the purple egg gave us these 4 purple spiders, these x coordinates, whereas the red egg for theta in quadrant 4 gave us these guys on the upswing. I would have played a clip from the film Arachnophobia with Jeff Daniels and John Goodman, but the idea is that these big spider eggs for theta, each of them breaks up into 4 spiders for x. So these 2 eggs here give us 8 spiders over here, corresponding to the 8 intersection points, the 8 x coordinates for the 8 intersection points between the purple and blue graphs. 1, 2, 3, 4, 5, 6, 7, 8. From pi over 3 to 23 pi over 12. More on solving trig equations next time.